Here in this problem, we want to find the reagents to plan the synthesis of these compound. And notice that it's not a single compound, really is a racemic mixture. It's two enantiomers that I produce. So first, let's find out how many carbons do we have in the product and in the reactant. So here we have 2 carbons, and here you have 1, 2, 3, 4, 5, 6. We have 4 more, so we need to come up with a strategy to add that. And this is, let's name that, this is a hexanol, so it's 4 bromo, 3 hexanol, but we have 2 chiral centers, so we need to specify the absolute configurations of carbons 3 and 4. And so carbon 3 configuration, I'm doing that so that you guys review how to determine absolute configuration. So here, priority 1 is the OH, second priority is the change where you have a bromine, so 1, 2, and 3, that is R. 3, carbon 3 is R, and the second will be S. So if you have trouble finding out absolute configurations, you can find my videos on that. So again, highest priority is bromine, then the other change to the right, then the one here going in this direction, but you're looking at that incorrectly. The lowest priority group is towards you, so we need to invert that. So it's 4S. All right, so that's the compound that I want. And it also produces the enantiomer to that. That's what En means. Okay, so I have 6 carbons here, I have 2. So I need to add more carbons to the chain. So what is the strategy here? So we're gonna do the reaction of this compound. If we add sodium amide, and then we add, say that we add ethyl iodide, then here's 2 carbon in the ethyl group. So we will form 1, 2, 3, and I add 2 more carbons, and I can repeat that. I have 4, and I need to repeat those steps so that I can make, so again, sodium amide, follow again by ethyl iodide. Ethyl iodide, and now I will have the number of carbons that I need. So I have these, plus 2 more, and 2 more. So again, this it has 1, 2, 3, 4, 5, and 6 carbon, and this will be 3-hexane. Okay, now I need to go from here to here. So there is a reaction. What reaction will help us introduce a bromine and an OH, but also opposite to each other? So that reaction we have studied with alkenes. We know that if we had an alkene, and say that I start with the cyclohexene as an example. If I have an hexene, cyclohexene, and treat it with bromine in water, I will make this reaction goes via bromonium intermediate, and let's throw it, because it's via bromonium intermediate, that is a plus sign, okay? And then you will have the nucleophilic attack by water. We have done that in several problems before. So you will produce the anti-product. So you will have here bromine, and here you will have OH, the attack on the back side. So here, opposite side, that plus the enantiomer. So that's what we have. But to be able to do that, I need to transform the alkyne into an alkene. But what type of alkyne will ensure me to do that? So in this case, the alkene. So in this case, we're going to be using, let's write it here, sodium and ammonia, which gives you a partial hydrogenation, but you will form the trans isomer. So here we have 1, 2, 3, 4, and 3, 4. So that is the alkene that you will have. And again, so 1, 2, 3, 4, 5, 6. So here you have 3 hexene. And then to go and form the final product, what I need to use is what I have here. So bromine in water. So summarizing, what have we done in this reaction? First step was noticing that the number of carbon had changed. We have 6. We need to add 2 more, 4 more. So we did 2 consecutive reactions in which we have removed acidic hydrogen here with sodium amide. We had made it react via SN2 with ethyl iodide. We added 1 ethyl on one side. We repeated that. And then we do a partial hydrogenation, but this time we use sodium metal reduction with ammonia, liquid ammonia, and that will produce the trans alkene. And then we will do bromine in water to give us the final product. And again, remember that we will have a mix of enantiomers on that reaction. So that is the general strategy to make that compound.